The last two sections of chapter 6 are very similar. In fact, it's hard to kind of cut them off at where one stops and the other starts. It's a lot of practice of using logarithms and looking at different equations and different formulas for using it. So to start with, natural logs versus something called a common log. The common logarithm is base 10. And so we're going to kind of start with that. I've mentioned base 10 quite a bit because that's what calculators work with. We'll also talk about natural logs in a little bit. So yeah, the common logarithm, base 10. So you might see something like this, log base 10 of 1,000 equals x. You might also see it like this. So if there's no base at all, if it doesn't list a base, it's automatically base 10. And that's just called the common logarithm. Calculators are based that way. That logarithm book that I had is based on logarithm base 10. And so that's the common log. So if you don't see a base and it says log, it's automatically base 10. So it works in the same way. We could rearrange this, saying the base of the logarithm is 10. So 10 to the x equals 1,000. Can flip-flop the domain and range and see that 10 to the third power is 1,000. Here, there wasn't a base, but it's assumed it's base 10. So 10 to the x power equals 1,000, same idea. We still get the same result. And so that's what the common logarithm is. It just means if they don't list a base, it's automatically base 10. Here's an example of a problem that you might see. I'm not going to read it word for word. I'll let you do that. But it talks about the U.S. Government testing nuclear bombs. I believe it was nuclear bombs, atomic bombs. And so the Bikini Atoll, I'm saying that wrong, I'm sure. Historians, you can slap me later. In the Pacific Ocean was used for these different tests. One of the times when they tested this atomic bomb, the earthquake, or what it seemed like an earthquake, was measured at a 5.0 on the Richter scale. So if you've heard of the Richter scale, that's how we measure the magnitude of earthquakes. So in 1906, there was an earthquake in San Francisco that had a magnitude of, estimated magnitude of 8.3 on the Richter scale. And we're going to try and compare these because it appears that the San Francisco earthquake was about 3.3 bigger, whatever, not times bigger, but 3.3 bigger, whatever that means on the Richter scale. And we're going to try and figure out what that, how that really shows up. That was a terrible way of saying it, but here we go. So here's the formula. And sorry, they give you the formula right here. M is the magnitude of the earthquake. So that's that 5.0 or that 8.3 magnitude. And that magnitude is measured on a logarithmic scale, where T is the number of times the shock wave is greater than the smallest measurable shock wave. So just your normal stuff when you're walking around and the earth is shifting and moving has a shock wave of something, and it's super small. And then a Richter scale of 5 is going to be some times bigger than that. That shock wave is going to be some amount bigger than that smallest measurable shock wave. Okay, so here's our formula. M equals log base T. They told us that the magnitude of the atomic bomb was 5, and the magnitude of the earthquake was 8.3. So if we plug that into the formula here, 5 equals log of T, 8.3 equals log of T. So we got the atom bomb, and we have the earthquake. And if we want to figure out how many times bigger, so that last question, the word problem, asked how many times bigger was the earthquake compared to the atomic bomb? And it's not simply 5 times something equals 8.3, because it's not that straightforward. We have this logarithmic scale involved. So what we need to do is change these logarithm numbers into decimal numbers, numbers that are just our normal numbers that we have. So 5 is some logarithmic number. It's 5 on the logarithm scale, and 8.3 is a logarithmic number. So if we're going to compare them, we need to change them into more decimal numbers. So the base here of both logs is base 10. So we can rearrange these into an exponential function and say 10 to the 5th. That's the shock wave. So the shock wave of this Richter scale 5.0, the shock wave from this atomic bomb, is 10 to the fifth power. And the shock wave for the earthquake in San Francisco is 10 to the 8.3 power. So you can plug those into a calculator. But the question that we're being asked then, so now that we have these as just the shock wave, 10 to the fifth and 10 to the 8.3, now we can compare those shock waves and say something times 10.5 is going to give us, or 10 to the fifth power is going to give us 10 to the 8.3 power. We want to know how many times bigger is 8.3, 10 to the 8.3 than 10 to the fifth. So if we want to compare those shock waves, we can solve for x. The earthquake in 1905 in San Francisco was about almost 2,000 times bigger, 1,995 times bigger than the earthquake or the shock wave produced by the atomic bomb test in the 1950s. So the atomic bomb test was much, much smaller, not just 3.3 smaller, comparing 5 to 8.3, but it was almost 2,000 times smaller. The earthquake in San Francisco was almost 2,000 times bigger than the shock wave that was produced by the atomic bomb. So to compare these, we have to use that formula to get the shock wave by itself, and then we can compare those shock waves by division. So that's one way that logarithms are used commonly. Another place that we see logarithms quite a bit is in chemistry, where you're talking about the pH, or the acidity, or the base of a solution. So like vinegar, orange juice, milk, I'm trying to think of other things that are acidy, apples, tomatoes, all that kind of stuff, how base and how acidic it is. So here's the equation, the formula for it. You won't have to memorize these, you'll have them in notes, but there will be a question on the test about pH. I believe I give you the formula. In fact, I'm going to go ahead and tell you right now that all the test questions have the formula in them. So as part of the question, it will tell you the formula for the magnitude of a earthquake, or the formula for the acid or base of a solution. So in this formula, pH is the acidity. H plus here is the concentration of hydrogen ions, and that's in moles per liter. Look back into your chemistry stuff for what a mole is, Avogadro's number. And here's the equation. So we had two problems. I'm going to ask you to try these two problems. I'll go through it right now, but I want to ask you to maybe pause it. Try to fill in the blanks in that formula and answer these two questions. I'm assuming you paused it. I'm assuming you tried it on your own. The first one, find the pH of orange juice. We got fairly acidic. If the concentration of hydrogen ions is 6.5 times 10 to the negative 4. I asked you to round your answer to the nearest hundredth. So I'm going to go over to the document camera. It was 6.5 times 10 to the negative 4, and that was the hydrogen ions. So if this is my formula, and now here I've forgotten it already, 6.5 10 to the negative 4. Okay. So if this is our formula, the hydrogen ions was 6.5 times 10 to the negative 4. That's how many hydrogen ion concentration in moles per liter. And I want to know the pH. So that's I just want to type that into a calculator. Basically, I've already got the pH by itself. I don't have to solve for anything here. So if I pull up my calculator and I do negative log of 6.5 times 10 to the power of negative 4, well, about 3.19, give or take. And so if we go back here, there you go, about 3.19. That's our concentration, that's our pH level. Find the concentration, so this is going the other way, then find the concentration of hydrogen ions in a glass of wine if the pH is 4.75. I'm going to write our answer in scientific notation. So 4.75 is the pH level. So now using that same formula, the pH level was I forget things so quickly, 4.75, I think, yes, 4.75. And we don't know concentration of hydrogen ions. But we do know that it's base 10 because of this natural, or this common log, excuse me. So the common log gives us a base 10. So I can rearrange this into an exponential function, 10 to the 4.75. Oh, we have this negative here, actually. Before we can rearrange this, this negative has to be dealt with. One way we could deal with that negative, remember, that's like -1. So if you have that negative out front, maybe I'll zoom in here a little bit if I can. It's like a -1 times the log of the hydrogen ions. So I could divide by -1. So now I've got -4.75 equals the log H plus. And that does make a difference. So now I have a negative. So now I have 10 to the negative 4.75. Gives me my concentration of hydrogen ions. And that's not quite scientific notation. So I'm going to move over to my calculator here and just type in, let's see what 10 to then, actually, if you may have noticed, there is a 10 to the button right here, 10 to the power of -4.75. Hey, look at that. My calculator already puts it in scientific notation for me. Thank you, calculator. This E, if you see that E again, that E, capital E, is not like the lowercase e, which is Euler's number, Euler's constant. That capital E is the calculator's shorthand way of writing times 10 to the power of. So what this says, I'm going back over here then, is that 1.78 times 10 to the power of -5. That's what this capital E to the -5, that's what this means, times 10 to the -5. There's my scientific notation. So the concentration of hydrogen ions, 1.78 times 10 to the -5 is what I should get for that. And that's how you write that. One thing, and I'll mention this now since it shows up different, there doesn't seem to be consistency within the math community as to how many numbers you're supposed to put after the 1 point, whether you put 7783, whether you put 1.78, or whether you put 1.77827994, whether you put all of them. It kind of depends on how accurate you want it to be. Since the purpose of doing this is to shorten the size of the number, we want to write it in kind of a abbreviated way. I find that writing 1.77827941 to be tedious. Like, what's the point then at that point? So if you have two numbers after the decimal, that's fine. But if you want to write more, that's okay too. I would say at least 2 to the hundredths. But after that, there doesn't seem to be consistency in the math community. I think it depends on how accurate you want your answer to be. So I'll say, and I'll be more specific than in the questions, to the nearest hundredth. And I'm going to stop there for this presentation.